Okay, for this one, I have two esters, and I'm in basic conditions. And you see the O minus. Now notice, right, some maybe you picked up on this, you have to have a certain type of base for certain esters, right? Notice how this base, this O minus matches the esters, because if this did add in, right, we just get the ester back out. So you kind of choose these bases on purpose. So this is going to cause it to only deprotonate in alpha CH. And because these esters are the same, it doesn't matter which one I deprotonate. And if they're both esters, you wouldn't know which one to deprotonate, because they're both esters. So I'll put the minus there. So now I've turned this ester into a nucleophile. That means this is still electrophile. So I'm going to add my nucleophile right in there. So we did a proton transfer. Now we added in. Let's see if I can make sure I don't mess this up. Keep that the same. This is now added into where there's no minus, this and this, right? Now at this point, these electrons are going to come down, right? Because we have tetrahedral intermediate. Kick that out. So elimination. And that's going to give us this. So this is like the Claisen condensation, just these kind of ideas we use esters. Don't worry, I don't worry about the names exactly, but just the ideas that, big ideas here are same starting materials, so they're both equally reactive, they're both esters. The base matches the ester, therefore you know it has to deprotonate. Right? So it deprotonates, turns one into an enolate. That nucleophile reacts with the same ester, but now the electrophile adds in tetrahedral intermediate. Kick the electrons down. Elimination, you get this 1,3 dicarbonyl. That's that there. So let's say we're thinking about alpha CHs here. And so I just drew 3 carbonyls, ketone, ketone, aldehyde. And so when we say alpha, we mean this is the main carbon one bond away. So these are the alpha carbons. And they have to have hydrogens on them to be deprotonated. So first thing you gotta do is identify the alpha CHs. So in this molecule, there's 1, and then there's 3 more over here. On this molecule, there's none there, and there's 3 here. And on here, there's none there and none there. Right? So this actually comes back to like the first thing we learned about those hidden hydrogens. Can you still find them? So this ketone has 2 different types of alpha CHs. This ketone only has 1 type on one side because there's no hydrogens here. And this aldehyde has no alpha CHs. So you've got to be able to identify those kind of things. Now we can take this a step further with this one, right? We can talk about kinetics and thermodynamic enolates. So let's say I deprotonated it. I could have this kind of enolate, or I could have this kind of enolate. Now this one, the green one, is actually going to be my thermodynamic enolate. Why is that? Because it has a more substituted double bond. So that makes it more stable, like Zaitsev's rule. This one is going to be considered the kinetic enolate. Why? Because it is easier to make, had a lower activation energy. There's three spots it could grab an H from, right? So this is a kinetic enolate. So identifying alpha CHs and then even a step further, thermo versus kinetic.